Hello again and welcome. We are still on the unit on numbers, and today we will begin the third part or the third subunit, which is scientific notation, prefixes and orders of magnitude. So we will be tackling three areas or three concepts at the same time in this video. So let's hope we can go about this quickly. We've already looked at scientific notations briefly in video number 4. We will just be touching just a little bit more on it. And in fact, what I want to do here is to just give you a small trick to remember to use when determining the value of k as you write your values in scientific notation, okay? So this is going to be, in terms of scientific notation, this is going to be very, very brief, hopefully, and it will solidify your understanding of how to express numbers in scientific notation. But in addition, we will look at what we mean by prefixes and their use and why they make writing much easier than even writing in scientific notation. We will also look at what we mean by orders of magnitude. It's a means by which we estimate values without having to go into detailed calculations. Scientists use this a lot to estimate sizes. For example, if we want to estimate the size of the Earth in terms of, say, the mass of the Earth, that we would write as 10 power 25 kilograms. So it's a way of approximating without having to go into great detail, okay? The same way, the mass of an electron would be 10 power negative 30, for example. All right, so let's begin. Why scientific notation? If you are watching this video for the first time, let's start by understanding why we want to write numbers in scientific notation. What is the use of writing numbers in scientific notation? In order to understand this well, I want to start by giving examples. Right, look at this example. We are asked to, we are told that given the relation distance is speed times time. Don't worry about the formula if you do not study physics. It doesn't really matter. We're just going into calculation. So if we are told that distance traveled by a body is the speed of that body multiplied by the time for which it travels, then we can calculate the distance that it travels, right? So given the relation distance is speed times time, calculate the distance traveled by a car traveling at 40 kilometers per hour, that's how we write per hour, in 3 hours. So if this car is traveling at 40 kilometers per hour and it travels for 3 hours, what distance does it cover? Well, the formula there tells us that to find the distance, we just need to take the speed, which we have been given here as 40 kilometers per hour, and we need to multiply that by the time, which is 3 hours there. Easily, even without much detail, without using a calculator, it is very easy to tell that the distance traveled is going to be 40 kilometers per hour. This is another way of writing kilometers per hour, multiplied by 3 hours, okay? And clearly we can cancel h, and h was one is in the numerator, one is in the denominator, so we can cancel them, and we end up simply with 120 kilometers, right? So that is pretty straightforward. It is very easy to calculate, to conduct or to perform this calculation, because the numbers that are given are not ambiguous. They are easy numbers, they are easy to work with. Even if they were decimal, they may be to 1 decimal places or 2 decimal places, so the calculation is not going to be weird, okay? Here is another one. This is going to be our example 2, okay? According to Albert Einstein, the energy equivalence of a particle of mass m is given by E is mc squared. This is a famous equation that I believe all of us probably know, even if we don't know what it means. It is the equation that relates the mass of a substance to its energy. The energy, mass and energy are considered to be equivalent, as you will study in physics, hopefully later in MYP 5 or in the diploma program. Okay, so if this is the relationship between energy and mass, where c refers to the speed of light, then below are some data for an electron. We are told, first of all, the speed of light is that. Okay, those are 8 zeros. And we are also told that the mass of an electron is that. Okay? Well, now we need to calculate the energy of an electron which has got this kind of mass and has that kind of, and we are using the speed of light of 300 million meters per second. Well, if we are asked to find the energy of this particle, of course we can still do this calculation, okay? We can still handle this calculation, but there are problems that arise when we are dealing with these kind of weird numbers. When numbers are either too small, such as the mass of the electron, or too large, such as the speed of light. In fact, this is not very large. We'll see other larger values. So when it comes to doing this kind of calculation, it is possible for us to do it, but there are some things, okay? There are some things that will be very irritating. And what are these? One, clearly you can see that the first thing is that we have to look at the number. We are going to spend some time trying to find out how many decimal places are there, how many zeros are those, and how many decimal places are they, and then if we are going to multiply by this, how many zeros are here, and how many, how many digits do we have in total. So that in itself is irritation, because you have to spend some time thinking about just the numbers themselves. The numbers are either too small or too big. That's one. The second thing is there is also the issue of space. If we are going to write this down on a piece of paper, then is it going to fit on that piece of paper? If you're going to do this calculation manually, how easy is it going to be? It is easy to do it, but the fact that it is going to be a very tedious process makes it irritating. In addition, you also need the space to write the number, okay? You're going to have to write all the zeros. Okay, then in the process of calculation, you still have to write so many zeros. In addition to that, there is the space that you need on your exercise book, if that's necessary. You need that in order to do this calculation. So this is an irritation. Thirdly, if you are doing this on a calculator, then you still have to punch all those zeros in the process of calculation. So either way, working with numbers such as this, either very, very small or very, very large, can be very difficult. It is for this reason that we want a way to reduce writing, a way to find a notation that we can use to express this same number, but in such a way that when we use it in calculation, we don't have, first of all, we don't have to write so much, we don't have to type in so many zeros like that, we don't have to write so many numbers, and in the process of calculation, we will come up with a way of doing that calculation without too much work on our side, okay? So this is why we need to be able to write numbers in scientific notation. Okay, here are other weird numbers that will make life very difficult when you want to perform some calculation. And these are numbers that you will meet in physics almost in every case. Okay, so here we go. And so numbers like that, numbers that are either very, very large or very, very small, can be difficult to work with. The best way is to express them in a way that does not require so much writing and does not occupy so much space. And when calculations are due, it becomes much easier to perform those calculations. We use the laws of exponent to perform the calculation. So let's see then what we are talking about. Consider the following numbers. We start with the number 200. Well, we know that we can express 200 as 2 times 100, and 100 can be expressed as 10 to the power of 2. And therefore, 200 could better be expressed, well, because 200 is not so large like the numbers we've looked at, it might not appear relevant in this case, but believe me, it becomes better when it comes to calculation. So therefore, we can express 200 as 2 times 10 power 2. Similarly, 135 is actually 1.35 multiplied by 100. This you already know. And we can express the 100 as 10 power 2, so that 135 can be expressed as 1.35 times 10 to the power of 2. So similarly, other numbers can also be expressed in the same way. 52,000 could be expressed as 5.2 multiplied by 10,000, which is 5.2 times 10 to the power of 4. I can express all the other numbers like that. Look at that. So 0.00726 is 7.26 divided by 1,000, okay, which in turn can be expressed as this is 10 power 3, but if we take it up, it becomes 10 power negative 3. And therefore, 0.00726 can be expressed as 7.26 multiplied by 10 to the power of negative 3. And I have included other numbers and the way they would be expressed that way. Provided we leave the number that we write here lies between 1 and 10 and is not actually 10. Can be 1 but not 10. Provided we write this number, we start with this number, and this number lies between 1 and 10, and the number itself has the same digits as this one but lies between 1 and 10, this is what we would mean by scientific notation. So we can say that 200 in scientific notation, so these numbers, the numbers in the first column, have been expressed in scientific notation in the second column. All right? So any number n can be expressed. Any number n can be expressed as a times 10 to the power of k, where k is an integer power here of the base 10. Okay? So we want to see how to express any number in scientific notation. So there are easy rules to use to express a number in scientific notation. Okay, so what you see below there is the scientific notation. Let's see. Okay, so what's scientific notation? We are saying any number n can be expressed in the form n equals a times 10 to the power of k, where a is a number with the same digits as n and in the same order as n, but a must lie between 1 and 10. A can be 1, but a cannot be 10. But any number lying in between is acceptable. K is an integer value whose size or whose value depends on how many steps you need to move the decimal point on the number n so that it is on the number a. I'm going to explain this, okay? So that's what I've just said, where a is a number with the same digits as n and lying in the same order, but a must lie between 1 and 10 with the 10 excluded. So a cannot be 10, but a can be 1 or anything in between, okay? K is an integer whose value is the number of decimal positions we move when we make a from n. Of course, I'm going to explain this. So we'll use the notational scale to help us decide the sign of the number k, of the integer k. Okay, how do we decide the value of k? So n is going to be expressed as a times 10 power k, where a must lie between 1 and 10, and k must be an integer. Let's go. So if the number n that we want to express in scientific notation is lying between 1 and 10, then the value of k is always going to be 0. So if the number we want to convert, so if the number is 4, if the number is 1.2, this 1.2 lies between 1 and 10. 7.8 lies between 1 and 10. 5 lies between 1 and 10. So any number that lies between 1 and 10, if we want to express it in scientific notation, we will write a times 10 power k. K is going to be 0 because the decimal point does not move at all. For example, okay, so 5.1 can be expressed as, so the number we want to write here is a number that lies between 1 and 10 and has the same digits as that. Well, there is no other number lying between 1 and 10 that has the same digits as 5 and 1 and 0 other than 5.1 itself. So we can come here and write this as 5.1, and we multiply by 10 power 0. And why 10 power 0? Because the decimal point has not moved anywhere. The decimal point here of the number n is lying between 5 and 1, and here is also lying between 5 and 1, so it has not shifted any number of steps, and therefore we write here 0 number of steps. Okay, like that. Let's see another one. Here's another example. If n is less than 1, So n is lying between 0 and 1, so it's less than 1. If that's the case, if that is the case, then our value of k is always going to be negative. Okay, so if n is less than 1, or lying between 0 and 1, then our value of k is always going to be negative. Here's an example. 0.00314 is a number that falls in that blue region. Okay, if that's the case, it's lying between 0 and 1, then our value of k is always going to be negative. So now, how do we determine our value of a? Our value of a is a number with the same digits as n. This is our value of n, but our a must lie between 1 and 10. So same digits, 314, in the same order. So a number with the digits 314 in the same order has to be 3.14. So I'm going to write 3.14 must be the number lying between 1 and 10, having the same digits 3, 1, and 4 there. And now I have to ask myself, what's the value of k is going to be negative, but negative of what? It refers to the number of steps we have to move when we move the decimal point from where it is there between those two zeros to between 3 and 1, which is the case here. So how many steps are those? They are 3. So we will have to write here 3. So this is 3, but it is negative. Okay? Because the number we are trying to change into scientific notation is a number lying between 0 and 1, or a number that is less than 1, if you like. Okay? Let's see another one. So similarly, if n is a number that is greater than or equal to 10, if n is greater than or equal to 10, look at that. So n is anything greater than 10, equal to or greater than 10, then our value of k is going to be positive. Okay, here is an example. 14,600 is a number that is definitely greater than 10. And so when we write this, our a has to be a number that lies between 1 and 10, but has the same digits as this, and that would have to be 1. It would have to be 1.46, right? And now we have to ask ourselves, how many decimal places have we moved between this, between that? So that's the decimal point. The position of the decimal point is there, right? So how many decimal places do we move so that we put the decimal between 1 and 4, which is there? You should see that is 1, 2, 3, and 4. So we move 4 decimal places, and so this number here is going to be a 4. Okay, and because the number n is greater than 10, our value of 4 is going to be positive. And so 14,600 can be expressed as 1.46 times 10 to the power of 4 in scientific notation. Okay, so let's see what else. Express the following in scientific notation. Okay, 5. We want to express 5 in scientific notation. Clearly, 5 is already in this range here between 1 and 10. And for that reason, we want a number here lying between 1 and 10 with the same digit. So that is going to have to be a 5. Okay. And because we are not, the decimal point has not moved, the number is lying between 1 and 10, the value of k is going to be 0. Okay? What about 0.0081? Well, we need to move the decimal point right there between 8 and 1. So the number that lies between 1 and 10 with the same digits as 8 and 1 is 8.1. Okay? And we have moved 3 decimal places to make this. So this is going to be 3, but because the number we are writing is here, because that number is there, it's going to be negative, so we write -3. I hope this is making sense. What about that? You can pause the video and try to express 31,500 in scientific notation. If you've done it right, then the number we have here, which has the same digits as 31,500, is going to be 3.15 for it to lie between 1 and 10. Okay, and the number of decimal places moved, the decimal place is here on 31,500. The decimal place is just after the last 0 there, and you're going to move it so that it lies between 3 and 1. So those are going to be 4 decimal places, and because 31,500 is greater than 10, our k has to be positive, so we will write times 10, 10 to the power of 4, like that. Okay, pause the video and try that one out. If you've done it right, you should end up with a value of a of 1.0, because this number is less than 1 there. So we end up with 1.0451 multiplied by 10 to the power of, has to be a negative, and that is negative 3. Okay, what about that one? 0.6 should be easy. A number lying between 1 and 10 needs to be 6. Remember to pause the video and try before you see the answer. So it's going to be 6 here, multiplied by 10, because this number is less than 1, so we have a negative here. But how many decimal places have we moved? 1 decimal place, so I expect negative 1 here. So my answer is going to be 6 multiplied by 10 to the power of negative 1. Lastly, express 10 in scientific notation. If you've done this correctly, please pause the video and try it out. But if you've done it correctly, you should end up with 1 times 10 to the power of 1. Okay? Problem sets, similar problem sets can be found in the eWorkbook related to this chapter, Scientific Notation, Prefixes, and Order of Magnitude. I have attached the PDF of this eWorkbook in the comment section. So if you want to try out similar questions like this, please go ahead and do so, and let's see what you end up with. Okay, there are enough questions for you to play around with. All right, let's move on. So additional examples in measuring instrument, I think we've done this. All right, so if you haven't looked at these questions, please look at them and express these numbers in scientific notation. I already shared this in video number 4, but in case you have not watched that one, you can still do this here. This is an infrared thermometer. That is a voltmeter. Okay. Next is a thermometer, an analog thermometer. This reading is about 68. You could say 67. It's up to you. Doesn't really matter. Express the value in scientific notation. This is a pH meter. There is a reading there, 7.474. What is that value in scientific notation? Here is a micrometer, digital micrometer screw gauge. The reading there is 0.25000. Express that number in scientific notation. Here some solve problem. Again, we've done this, but let me just repeat it. If you go in and you meet a question like this, express the reading in scientific notation. So here is an instrument. It is showing a reading here, somewhere there. It is showing a reading there. What reading is that, and can you express it in scientific notation? So to answer this question, where we need to know the parts of this is called a micrometer depth gauge. The one we saw earlier was a micrometer screw gauge. So this one is used for measuring depth. The other one is used for measuring the length of short lengths or short distances, short thicknesses, and so on. Okay, so this part of the micrometer is called the sleeve. Okay, so we are going to take that reading, but first this area here, I've blown that up so that you can see it more clearly. This part is called the sleeve. This part is called the thimble. Okay, and so this is called the sleeve reading. Okay, so this is the scale here is going to be the sleeve reading, and that is going to be the thimble reading or scale. Okay, so if we are going to take a reading, we go to the sleeve reading, and if you look at this, you should be able to see that coming from this side here, that is 15, so that is 10, so there must be 5 somewhere around here, and there is a 0 somewhere there. So if we start from 0 and we're coming this way, you can see that this one here, we should be at 8 9, and then 10. So we have just passed 8. We've just passed 7. The other side is 7.5. So 7.5, 8, 8.5, 9, 9.5, and 10. So we have passed, we've not passed 7.5. So that's what you're seeing there. That mark there indicates 7.5. Therefore, we know that our value, our reading has passed 7, but it's not reached 7.5. So the sleeve reading is therefore giving us 7 point something. We will write that as 7.0. Okay, so then we will add something to it. That something that we have to add there is going to come from the thimble reading. Okay, so 7.0 from the sleeve. And then when we look at the thimble, we can see the reading starting on that side. So we have 5, then there is a 10 here. So there is 5, then that's 0.5, then this is 10, 15, 20, and so on. Now we use that dark line there. It's called the datum line. So that dark line there is what we use to take reading. It's like the arrow that is used to take reading on the thimble. And if you look at that black line there, it is pointing directly at 14. Check that carefully and see that the reading is at 14. So we can say that the thimble reading is indicating 14, which we shall read as 14/100, okay? Because the thimble is split up into 100 parts. So 14 parts in 100 is the same as 0.14, which is to say that the reading as given by the thimble is 0.14 millimeters, which is to say the bit that is remaining down there from 7, before we get to 7.5, is just 0.14. So we'll need to add that to 7.0. So the reading there is 0.14, and so the reading being indicated as the depth being measured by this is actually the sum of those two, which is recorded as 7.14 millimeters. But we are told to express our answer in scientific notation. 7.14 lies between 1 and 10. Therefore, in scientific notation, A is just 7.14. The decimal place has not moved. Therefore, our answer is 7.14 times 10 to the power of 0. I hope that is clear. All right, let's move on. So that brings us to the end of discussion on scientific notation. Please look at the questions in the eWorkbook and see if you can answer them. Let us know if you have difficulties with any of those questions and we can go through them together. Put a comment, place your comments in the comment section, or send me a message and I will be able to help you with a question. All right? The next video is going to be actually a solution to a selected number of questions from the particular workbook. Okay? Now let's go to the next thing, which is the idea of orders of magnitude. Okay? Orders of magnitude are a convenient way of estimating values of products or just numbers without detailed calculation. So if somebody was to say, what is the mass of a full-grown man? Well, different men have different masses because we have different sizes, okay? But there is a value that if you gave for a full-grown man, for a general fully grown man, the mass is probably going to be of the order of 10 to the power of 2. So there are people, 10 to the power of 2 is like 100. Okay, there are people who will be heavier than 100. There are people who will be much less than 100 kilograms. In orders of magnitude, we will say that a man, a full-grown man, is about 10 to the power of 2 in orders of magnitude. We will see how we end up, or how we arrive at that value, so that a person who has a mass of 70 in orders of magnitude has the same mass as someone who has a mass of 140 kilograms, for example. Okay? So orders of magnitude. Then, example, we can be given a calculation such as this one, something to work out, an expression such as that to calculate. And by just scanning through it like that, I can tell directly that in orders of magnitude, this is 10 to the power of 3. So then the question is, how did I arrive at that quickly? So approximately, the answer to this product here, or this expression here, is going to be approximately 10 to the power of 3 in orders of magnitude. The exact value is of course going to be different, but in orders of magnitude is approximately 1,000. Okay, approximately 10 to the power of 3. Okay, similarly, if we were asked to express this in orders of magnitude, that is 4.5. This is 10 power 1, so I'd say this is 10 power 1, 10 power 1, 10 power 1, so that's 10 power 3, and so the total is 10 to the power of negative 2, like that. Okay, here's another one. In orders of magnitude, what's the mass of a full-grown man? So 70 kilogram should be 10 to the power of 2. The question is, how am I coming up with these values? And that is what we want to discuss. Expressing numbers in orders of magnitude can be very, very useful when we want to estimate values of things that are either very, very tiny, like we saw in that table, or quantities that are very, very large. I gave an example of the mass of the Earth, or the mass of an electron, or the time it takes an electron, the time it takes light to travel through the nucleus, or the time it takes the light to come from the sun to the Earth, and so on, or the distance to the sun, distance to the moon, and so on. So such values can be expressed in orders of magnitude because we will usually not be interested in the nitty detail of the exactness of the value. Okay, so consider the following numbers: 1, 10, 100, and 1,000. We can express all these four numbers in powers of 10. So 1 can be expressed as 10 to the power of 0, 10 can be expressed as 10 to the power of 1. We are expressing them in powers of 10. Okay, 100 can be expressed as 10 to the power of 2, and 1,000 can be expressed as 10 to the power of 3, and so on. In fact, any number can be expressed as 10 to the power of an integer. Okay, approximately as 10 to the power of an integer. So the numbers 0, 1, 2, and 3 are referred to as the orders of magnitude of the respective numbers. So 10 in orders of magnitude is 10 to the power of 1. 1,000 in orders of magnitude is 10 to the power of 3. Okay? But it is not limited to, 1, 10. It's not limited to numbers with zeros like this. We can express 57 in orders of magnitude. We can express 500 in orders of magnitude as well. Okay? So in fact, any number n can be expressed as 10, approximately as 10 to the power of m, where m is an integer. Okay, so if we can express a number as 10 to the power of m, for example, the number 4, I'm going to write this here, the number 4 can be expressed as 10 power 0.602, but 0.602 is not an integer, but I can round this up because it's greater than 0.5. I can round this up and write this as approximately 10 to the power of 1. So 4 in orders of magnitude is 10 to the power of 1. The question is, how am I ending up with this number here? How am I getting the number? 2 can be expressed as 10 to the power of 0.301, which is approximately, this number is 0.3 is less than 0.5, so this rounds down to 0, so this is 10 to the power of 0. Okay, so 2 is in the orders of magnitude is the same as 10 to the power 0, but 4 is in orders of magnitude the same as 10 to the power of 1. The question is, how am I ending up with these numbers here? And that's what we want to discuss. So in fact, any number n can be expressed as n is approximately 10 to the power of m, where m is an integer. Okay, so if it is a decimal number, then we have to round it off to an integer. Okay, let's see what we are talking about. So 500 is the same as 10 to the power of 3. We will see that. And 0.00056 is the same as 10 to the power of negative 3, like that. And 13 is the same as 10 to the power of 1 in orders of magnitude. Okay, so this is a way of approximating or estimating values. 3 is equivalent to 10 to the power of 0, but 3.2 is equivalent to 10 to the power of 1. Why is that? Why is 3 the same as 10 power 0, but 3.2 is the same as 10 to the power of 1? Okay, determining the orders of magnitude. We can use a calculator to find the orders of magnitude of a number. Because we haven't gone into a discussion of logarithms, which is a topic in mathematics, we are just going to use a calculator directly to see what we mean. All right, so we can use a calculator to find the orders of magnitude for any number. Okay, to do so, all right, so any number n can be expressed as 10 to the power of m. How do we find m? Okay, m is the log to base 10 of n. So we will go to a calculator and press log to base 10, and then we will put our number, and that, if we put that number, we will get what m is. I'm just going to explain that there. So on the calculator such as this one here, the log can be found here. So this is log to base 10, but if you want to find log to another base, you would use that one. So we will use that log thing there on the calculator to determine the value of m for any number. Here is an example of what I'm talking about. Express the following in orders of magnitude. So the first one there is 7. So if we're going to find the 7 in orders of magnitude, the first thing we need to do is go to our calculator and work out log to base 10 of 7. This is the number that we want to express in orders of magnitude. So find its log to base 10. If you do that, I think it's 0.848, I think 748 or something like that. So we need to write this as 10 to the power of log to base 10 of 7. This is going to be our value of m there. So if you do that, you should find 0.845. So the log to base 10 of 7 is 0.845. Now 0.845, if we round it to an integer, it's closer to 1 than it is to 0. And so we can approximately say that 7 is 10 to the power of 1 in orders of magnitude. I hope you're understanding this. Okay. Another one, let's express 57 in orders of magnitude. So the first thing we do, we will express this as 10 to the power. In other words, we look for the log to base 10 of 57 and we will put it as the power of that. So log to base 10 expresses a 10 power, log to base 10 of 57, and if you do that, you will get 10 to the power of 1.756. Okay, so this you get on the calculator directly, and then we round off that number there to the nearest integer, and that becomes 10 to the power of 2. So 57 is 10 to the power of 2 in orders of magnitude. Okay, let's see another one, 0.14. So to do that, we will express this as 10 to the power of the log to base 10 of 0.14. So what you want to do is go to your calculator and type log, go press that, and then enter this data here, 0.14, and whatever you get, you're going to put it as the power of 10 there. So if we do that, we get 10 power negative 0.854 again, and negative 0.854. If we round that off, you will see that we end up with negative 1, and therefore 0.14 in orders of magnitude is equivalent to 10 to the power of negative 1. Okay, please pause the video and try to express 0.0095 in orders of magnitude. Okay, right. So if you got that right, you should have ended up with log of that, which should give us 10 power minus 2.02, which is the same as approximately, if we round that to the nearest integer, we get 10 to the power of negative 2. So here are additional worked examples. Express the following values in orders of magnitude. All right, there are 3 questions here that I want us to answer. So we want to express 104 in orders of magnitude. We also want to express 0.817 and 5.6 times 10 power 13. the best way to do this is to first express that number in scientific notation. So if we write that, okay, so we want to express the number in scientific notation if it's not already in scientific notation like this. So that's not in scientific notation, so express it in scientific notation, and then we end up with 10 power 2, but this, we need now to express this number in orders of magnitude. The way to do that, so that's the number we want to first of all turn in orders of magnitude. So we are going to look for log to base 10 of 1.04 on your calculator, and so we'll write this as 10 to the power of that. Okay, enter log to base 10 of 1.04 on your calculator, and if you do so, you will end up with 0.017, which means we are going to express this as 10 to the power of 0.017. So now I have, so now that's what's going there. So I can now write that down here. That is 10 power 0.017, that is this one here. And now I can say multiply by this. So multiply by 10 to the power of 2. Well, we are multiplying similar bases, so by laws of exponent, the exponents are going to add up because we are multiplying the bases. So this becomes 10 to the power of 2.017. And now we can round that up or down to the nearest integer, and if you do so, we get approximately 10 to the power of 2. And therefore, 104 in orders of magnitude is 10 to the power of 2. Let's do that with the next question. So it is not in scientific notation, so the first thing we have to do is to convert it to scientific notation. This is just to make you understand what we are doing. After that, we really don't need these calculations. Okay, we'll see a faster way of getting to what we want. All right, so we've expressed this in scientific notation. The next thing is to pick this one here and write it in orders of magnitude. So we are going to calculate log to base 10 of 8.17, and log to base 10 of 8.17 is going to be 0.912. Try that on your calculator. So we will express 8.17 as 10 to the power of the log that we found. Okay, and now we take that and we add to this, so write them together. So the first one, 8.17, is 10 to the power of 0.912. Now we are going to multiply by this. Okay, and because we are multiplying similar bases, we add the exponents, so 0.912, and we're going to add -1. If you do so, you get 10 to the power of -0.88, like that. If we round this to the nearest integer, we end up with 10 to the power of 0. This number here is closer to 0 than it is to 1 or to -1. Okay, like that. 5.6 times 10 power 13 is already in scientific notation because 5.6 lies between 1 and 10. Okay, so the first thing we want to do is to change that, find the orders of magnitude of 5.6, find log to base 10 of 5.6. If we do that, then 5.6 becomes 10 to the power, so the log to base 10 of 5.6 is 0.748. So 5.6 can be expressed as 10 to the power of that. So now I will put that here and multiply by 10 power 13. Okay, so 10 power 0.748 multiplied by 10 to the power of 13 gives me 10 to the power of 13.748. If we round that off to the nearest integer, we get 10 to the power of 14. And so in orders of magnitude, 5.6 times 10 power 13 is the same as 10 to the power of 14. Okay? Now, like I've said, we don't always have to do all these calculations, as we will see. Let's answer these 3 questions here. So we really don't have to do all those calculations. Once a number is in scientific notation like this, we can proceed. We can tell the order of magnitude of a number such as this one without really wasting time. Here we would still have to write it in scientific notation. Once it is in scientific notation and this number lies between 1 and 10, then it is very easy to determine the order of magnitude of this. And the way to do that is to try and find what is 10 to the power of 5, because we know that if a number, let's see here, let's go back, we found that if this number is greater than 0.5, then we round it up. Okay, it is the power that we are, the exponent that we are rounding here. If it is greater than 0.5, then we take it to 3. If it is less than 0.5, then this remains as 2. Okay, so 0.5 appears to be at the boundary. So if a number is, if it is 10 to the power of 0.5 or more than 0.5, then we will take it to 10 power 1. If it is less than 0.5, we will reduce it to 10 to the power of 0. So that's all we need. Now, what number is it? What number do we get when we take 10 to the power of 0.5? If we know that number, then that becomes our boundary, and we can always use that number to determine the order of magnitude. And here we go now. Okay, so this is what we are saying. Okay, the boundary is at 3.162277 and so on. So 10 to the power of 0.5 is 3.162277. What we are saying is that 3.2, for example, will be greater than 0.5 here. And if it is greater than 0.5, then we will be rounding up. If it is less than 0.5, so 3.16 without the 0.22 is going to be less than 0.5. And so we will have to round it down. What am I saying? That when I see this here, I know that this is going to be greater than 10 power 0.5. Okay? So because of that, this is going to be rounded to 10 to the power of 1. This number here is greater than 3.166, so this is going to be rounded up. So this is 10 power 1, that is 10 power 1. 3.8 is, I'll change this to 3.8, this is going to be 3.844 times 10 to the power of 5, right? So 3.844 is greater than 3.16, so it's going to be rounded to 10 to the power of 1. This is what I'm saying. So this, if I were to look for, I can do that right now. What is the log to base 10 of 6 point? I'll use my phone quickly. I have a calculator on the phone. So if I find the log, I'm looking for the log of 6.68. Okay, and if I find that, I get 0.824. 0.824, it means that this thing here is going to be 10 to the power of 0.824723. Okay, so clearly this is going to be greater than, this is going to round to 10 to the power of 1. So I'll say that, I think I wrote that poorly. Okay, so this is going to be 10 to the power of 0.824 or 23. Okay, and then I'm going to multiply by 10 to the power of negative 27. Already this rounds off to about 1, and so if I work this out, I will get 10 to the power of 1 times 10 to the power of minus 27, which becomes 10 to the power of minus 26, like that. So I don't really need to, I already knew this was going to round off to 10 power 1 because I know 6 is greater than 3.16, like that. So if I know, so I will use 3.16 as my boundary. Any number that is greater than 3.16, I'll write that as approximately 10 to the power of 1. Any number less than 3.16, I'll write that as 10 to the power of 0, like that. And so I know that 6.68 is approximately 10 to the power of 1, and multiply by 10 to the power of negative 27, that's going to give me 10 power minus 26. So immediately I know that in orders of magnitude this is going to be 10 power minus 26. Okay, I already know that this 5.12 is greater than 3.16, so this is also going to be 10 to the power of 1, and I'm going to multiply that by 10 to the power of negative 10 This is the volume of the sand particle approximately, and so approximately this is going to be 10 to the power of -9 as orders of magnitude. Okay, what about the last one? This is 3.8. That is 3. Sorry, in fact I can solve it here. Okay, so that one there is, I can write it as 3.844 multiplied by 10 to the power of 5. So I want to express that in orders of magnitude. I know 3.8 is greater than 3.16. Okay, so this can be rounded up to 10 to the power of 1. And I'll multiply that by 10 to the power of 5, and I end up with 10 to the power of 6. So very, very quickly we can tell the orders of magnitude without having to waste so much time with the previous calculation. Okay, so use this boundary to tell you whether to round to 1 or round back to 0 once you've written a number in scientific notation. Let's see this in other questions as well. Okay, so here we go. Here is an expression. We want to find this in scientific notation. So the first thing we do, I look at that there and I can see this is 6.68. It's greater than 3. I believe I have that figure still added there. There you go. It's greater than, this is greater than 3.16. So immediately I'll write this as 10 to the power of 1. This one here. This is less. So this is less than 3.16. So this is going to be 10 to the power of 0. Okay, 31 is, can be, I think let's do it neatly. Perhaps it's going to help to do it neatly. So I have I'll write here 6.68 multiplied by 10 power minus 27. Then we are multiplying by 31.4 in scientific notation is 31.7, sorry, times 10 to the power of 1 in scientific notation. Okay, we can write this 28 in scientific notation. We end up with 2.8 multiplied by 10. I think I can use a different color. 0.8 times 10 to the power of 1. That's just 28. Then times 10 to the power of 4, which is already here. Then we have times 1.8 times 1.80 times 10 power negative 2. So as I was saying, this here is greater than 3.16 there. So this is going to be 10 to the power of 1. Okay. This is also greater than 3.16. So I'm also going to express this as 10 to the power of 1. Yes. This is less than 3.16. So I'll express this as 10 to the power of 0. Right. And this is also 10 to the power of 0. So the numerators, I have power 1, power negative 27 is power negative 26, power 1 there, power negative 25. Alright, so basically I have, what I have, it's a bit disorganized, it's 10 power 1 times 10 power minus 27 times 10 to the power of 1 times 10 to the power of 1. So 10 to the power of 3 and 10 to the power of negative 27 is basically 10 to the power of negative 24, but we can wait. This is 10 power 0, this one here. Okay, then we have times 10 power 1 times 10 power 4 times 10 power 0 and times 10 power negative 2, like that. So you can see that what we end up with here in the numerator, it is 10 power negative 24 because there is positive 3 there and 27 there, negative 24. And in the denominator is 0, 1, 5. 5 minus 2 is 10 power 3, 10 to the power of 3. and then I can bring that up and I have 10 to the power of negative 27, like that. And so in orders of magnitude, this thing here reduces to 10 to the power of negative 27. It's not so organized. I think I prefer to type it, but hopefully you've understood what we have done. Okay. Try it out and be sure that you're getting the same answer. If you are an international baccalaureate IB, that is diploma physics student, then orders of magnitude is a must. So hopefully this helps you as well. Let's go to the next thing. Now we start prefixes. So just to complete what I was saying, if you're an IB physics student, ideas about orders of magnitude is paramount. It's a part of what is tested in, especially in paper 1, but it is also going to turn up in paper 2 in various instances. Okay, so you need to know how to express numbers in orders of magnitude or how to estimate values in orders of magnitude. A very typical question is usually the mass of an electron, which is 9.11 times 10 power negative 31. So if it is 9.11 multiplied by 10 to the power of negative 31, then 9 is greater than 3.16, so I can write this as 10 to the power of 1, okay? Then multiply by 10 power negative 31, and we end up with 10 to the power of negative 30 kilogram. So in orders of magnitude, the mass of an electron is 10 to the power of negative 30 kilograms, okay? So such questions are very, very common. The ratio of the size of an atom to the size of the nucleus is of the order of 10 to the power of 5, and so on. Okay, so orders of magnitude are a must for an IB physics student. Okay, so let's look at prefixes. Now, we've learned that the scientific notation helps us compress a very, very large or a very, very small number. In other words, in order so as not to write those so many zeros, we can compress and write a number in scientific notation. So scientific notation is very useful for that for various reasons. I think there are at least 4 reasons why we want to express a number in scientific notation. Makes calculations easier, reduces writing, reduces typing, reduces having to think about simple numbers, over a long period of time just because you're counting numbers, and so on, right? Reduces space that you use when you have to write on a piece of paper, and so on. So the scientific notation is very, very important for compressing a rather large number or a very, very small number into a small space like that, okay? The use of prefixes actually even improve that writing. It helps us write the same number so that we even use less writing than in scientific notation, and that's why prefixes become important as well. Well, I am sure we've all met prefixes, even if we didn't know that we refer to them as prefixes. For example, here are some numbers, and here is the way they are expressed in scientific notation and the way they are expressed with prefixes. Think of a number like that. So what is that? That is 2,300,000,000 bytes. Okay, this is computer units. Okay, so in scientific notation, that would be 2.3 multiplied by 10 to the power of 9 bytes. Now, scientific notation is great because we have, we didn't write all those zeros. Okay, if there were more, even better. But now we also don't want to write this 10 power 9, so we can replace 10 power 9 by something that we all agree on. So 10 power 9 is usually referred to as giga, all right, or G. And so instead of writing 2.3 times 10 power 9 bytes, I can write 2.3, I can write this, 2.3 gigabytes. Okay, so the G here takes the place of the 10 to the power of 9 and even the multiplication sign, because we know it is there. Okay, so 2.3 gigabytes is the same as 2.3 times 10 power 9 bytes, and 10 power 9 means 9 zeros. Okay, and so that can replace that number there. So we've moved from writing a huge number like this to compressing it into scientific notation, which is good, especially for calculations. We need this and not this. In calculation, we need this. But if we just want to express it for somebody to read it quickly, then we can reduce by replacing the 10 power 9 by a symbol that we all agree to use to mean the same thing. So that symbol, G, is a prefix, okay? So the G, which means giga, comes before B, okay, comes before the byte to replace 10 to the power of 9, okay? Here's another one. 400 meters, the M is in yellow. 400 meters can be expressed as, in scientific notation, 4 times 10 to the power of 3 meters. That M there is the same M there for meters. Okay, and we can remove the 10 to the power of 3 and replace it with this lowercase k. And the lowercase k means kilo. So the kilo comes before the M to replace 10 to the power of 3. Okay, so k means kilo. It will come before M to replace the letter, to replace 10 to the power of 3. One more example. We have 0.006 meters again. We can express this in scientific notation as 6 multiplied by 10 to the power of -3. Remember, this number must lie between 1 and 10. Okay, and then we check how many decimal places we've moved. Okay, we've moved 3 decimal places so that the decimal point comes in front of 6. All right, and because the number we are expressing in scientific notation is less than 1, this is going to be negative. K is going to be negative. So that's scientific notation. Now 10 power 3, power -3, is also given a special name in scientific work, and we refer to it as the milli. Okay, and so we can write this as 6 millimeters. Okay, 6 millimeters. The M that the first M there, which in this case I've made green, is a prefix. It comes before the yellow M there to take the place of 10 to the power of -3 there, like that. So once again, M for milli comes before M to replace 10 to the power of -3. So effectively what we are saying is that by definition we know that a prefix is a word or letter that comes before another, and we just saw, so these letters, the G, K, and M, which came before M there and B there, these are called prefixes. Okay, they have special names. The prefixes have got special names that we use for them, and I want us to take a look at them. Okay, so a prefix is a word or a letter that comes before another. For example, the kilo in kilometers. So when we write kilometers, the kilo comes before the meter, is a prefix. Okay, and it's used to represent 1,000. So kilo is a prefix that is used to represent 10 to the power of 3 or 1,000. Okay, below is a table of prefixes and the values that they represent. Okay, so you will be required to know these prefixes and the numbers they represent, but there are certain special ones that you truly need to remember. The others are not so much, but some of these here are going to be important. So 10 power 9 is represented, which is basically 1 billion, is represented using the prefix giga. And the symbol for this prefix is capital G. So you can't use small letter or the lowercase g to represent giga. Okay? So the uppercase G, as the example we looked at, which was gigabytes, for example. Then we have 10 power 6. We don't worry about power 8. So this goes in powers of 3 until we get close to 1. So 10 power 6, which is basically 1 million, has got a prefix which is mega. So mega means a million, and the symbol we use for mega is capital M. So megabytes, right? Next one is 10 to the power of 3, which we've also looked at, meaning 1,000. We use the symbol kilo, and this time it's lowercase k. So whether it's uppercase or lowercase is really important. Do not use capital K if you want to say kilo. All right, don't use lowercase m if you mean mega. If you use lowercase m, then you mean milli, not mega. Okay? Then we have 10 to the power of 2, which is 100, is called hecto, and we use lowercase h. All right, then we have 10 power 1, which is the same as 10, means deca, lowercase d and a. And 10 to the power of 0, which means 1, does not have any prefix. So we will leave that out. Okay, so these are positive powers of 10. But we also have lower cases. So on the positive power side, the most important ones are the kilo, the mega, and the giga. So the first three are the ones that you really need to remember. You need to remember that kilo means 10 power 3, mega means 10 power 6, which is a million, and giga means a billion. Okay, on the other side, we have 10 power negative 1, which means 0.1, and which means deci. Okay, useful in chemistry. We use lowercase d. 10 power negative 2 should be familiar, and it's going to be one of the ones you must remember. 0.01, which means centi. Like when we say centimeters, we mean times 10 to the power of negative 2 meters. So lowercase c. Then we have 10 to the power of negative 3, which should also be familiar. 0.001, that is the milli, 10 power negative 3. We use lowercase m. So the lowercase m is used for milli, the uppercase m is used for mega, and you should not use them just anyhow. 10 to the power of negative 6 is 0.000001, which is called the micro, and the symbol is the Greek letter mu. So that letter there refers to mu as is in the Greek alphabet. Next is 10 power negative 9, okay, which is that, which is the same as nano. So on the lowercase side, you need to remember all the way from 10 power negative 2 to 10 power negative 9. If you happen to be a chemistry student, then you also need to remember 10 to the power of negative 1. Okay, so you need the first three here. You must remember the first three, and the rest, the ones that are negative. Okay, so when you see this in an expression, if you see a unit expressed with a giga or milli or micro and so on, you should know what the microbit refers to. Let's see how this becomes useful in calculation. 10 power negative 12 is called pico. We have 10 power negative 15, which is femto. And then we have 10 to the power of negative 18, which is atto, but we will leave these ones out, so we stop at pico. If you're a physics student, later in DP2, we talk a lot about pico, especially when we discuss capacitors and the charge they store. All right, let's look at, we will ignore that until we get to calculation, but let's look at the use of the table in determination of prefixes. Here is an example. How many grams are there in 1.5 kilograms? So we have 1.5 kilograms. We want to know the number of grams there are. So we start by 1.5 kilo is the prefix. Now if you go back to the table, you should see that kilo there means times 10 power 3. In other words, times 1,000. And therefore it's just 1.5 multiplied by 1,000, like this. In other words, we remove the k and replace it with the 10 times 10 power 3, and we see that we end up with 1,500 grams. So 1.5 kilogram is the same as 1,500 grams, just like that. Okay, so you can change from one multiple unit to another if you know the meaning of kilo, milli, and so on. If you know the meaning of the prefixes, you can use them to change the units accordingly. Here's another one. How many seconds are there in 624 centiseconds? Now once again, if you go back to the table, you will see that centi means 10 to the power of negative 2. And so 624 can be expressed as, we replace the c with times 10 power negative 2. And if you multiply that, that's the equivalent to dividing by 100, right? Because it's 624 over 10 to the power of 2, or 624 divided by 100, which should be 6.25 seconds. All right, so we replace the C with 10 power negative 2, and so our answer is in seconds, like that. Okay, here's another one. Bacteria have a length of 0.3 micrometers. Find the length of the bacteria in meters. Okay, please pause the video and see if you can answer that question. In fact, I haven't answered it, so I leave it to you to solve that one. You can make use of the table, so scroll back and see what these values are. But of course, this is also on the table is in your workbook. So if you go to the workbook, you'll find the table. I can't remember what page it is, but it is there. You can always check as you try to solve these questions. Okay? Right, here are other questions on spatial dimension. That means in terms of volume, space that is occupied by an object, could be area and volume. So here is one question. It's a rectangle. For the rectangle, find the area in square millimeters, and part B requires you to find it in centimeters squared. Okay, so the width is 3.5 millimeters and the length is 8 millimeters. So the area is given by length times width for a rectangle. So we are going to say 8 millimeters multiplied by 3.5 millimeters. So we'll multiply the numbers and then we multiply the units. So 8 multiplied by 3.5, I think, is 28. Okay, and then we have millimeters times millimeters is going to be millimeters squared. Just like that there. Okay, so therefore our answer has to be 28 millimeters squared. You can use a calculator if you must, but you really don't need a calculator there. Okay, so that's how we find the area of the rectangle in millimeters. Okay, now the next one is to find the area in centimeters squared. There are several ways of doing this. One of them is to change each millimeters to centimeters before you multiply, or work with what you already have and change that to centimeters squared. So using the one method, 1 centimeter, or let's say 1 centimeter is the same as 10 millimeters. Okay, therefore we have millimeters squared, so 1 millimeter is the same as 1 over 10 centimeters. So if I square this, then I must square this. Okay, so 1 millimeter squared is the same as 1 over 100 centimeters squared. Therefore, 28 millimeters squared, which we found here, must be the same as 28 over 100, or times 1 over 100 centimeters squared, and we get 0.28, right, centimeters squared, like that. So this is one way of doing it. Yes, the other way to do it, so this is just one way we can do it. Work with this. 1 centimeter is 10, so divide both sides by 10. 1 millimeter is the same as 1 over 10 centimeter. Then square so that we end up with millimeter squared. So if 1 millimeter squared is this, then 28 millimeter squared must be 28 multiplied by this, which gives us that, which is that. Yes? Alternatively, we can do this. Alternatively, let's work out the area in centimeters squared as an alternative route. So the area is 8 millimeters multiplied by 3.5 millimeters. Okay, and we reason that 1 centimeter is 10 millimeters. Okay, if we rearrange that, the same thing we did, 1 millimeter is 1 over 10 centimeters. So 8 millimeters must be 8 times 1 over 10, so it's going to be 8 over 10 there, and 3.5 millimeters must also be 3 over 10 centimeters, like this. So we can write 1 millimeter is 1 over 10, so 8 is 1 over 10 times 8, so that we have that. So we multiply that also by that, we have 3.5 over 10 is another way of doing it, and so we end up with 28 over 100 centimeters squared, because centimeter times centimeter. Okay, we end up with the same scenario, and our answer is 0.28 centimeters squared. So that's another way of doing it. So choose the method or the path that you find easiest to follow, and that will be fine. Okay, right. Let's see another example. This is a cuboid, and the question is to find the volume of the cuboid. Okay, first in cubic millimeters and in cubic meters. So in cubic millimeters, this is in centimeters, so we have to change that. If we want answer in millimeters, we have to change anything that is in centimeters to millimeters. Okay, well, 1 centimeter is 10 millimeter, so this is equivalent to 3 millimeters, and that is equivalent to 1.5 millimeters. But let's do that. So part A, we start by saying 1 centimeter is 10 millimeters. So okay, I've shown a ruler there to help you see. So the distance between the point marker for 0 and 1 there is the same as 1 centimeter. And you can see it's split up into 10 smaller bits, which are called millimeters. So 1 centimeter carries 10 millimeters. Okay, so 0.3, if we are going to change that to centimeters, we have to multiply by 10, because 1 centimeter is 10 millimeters. So 5 centimeters must be 5 times 10 millimeters, which is 50 millimeters. So whatever you have in centimeters, you have to multiply by 10 to get the value in millimeters. And so I'm going to take that. So the volume of a cuboid is length times width times height. So length is 5, width is 0.3. So changed into millimeters, we multiply by 10. Then we say times 5 millimeters, which is already in millimeters, no need to change. But then we have 0.15 centimeter there, which needs to be changed into millimeters. So 0.15 multiplied by 10 millimeters. Okay, so that is 3 times 5 times 1.5. And if we work that out on your calculator, you should end up with 22.5 millimeters cubed. Okay, I hope you got that. The next one I actually want you to do, but let me just set you on the right path. Okay, we want to change that to cubic meters. So part 2, 1 meter is the same as 100 centimeters, which is the same as 1000 millimeters. So you can choose to change everything to meters first, or you can choose to change everything to centimeters and then change accordingly. All right. If you go backwards, divide everything by 1000, then you end up with 1 millimeter here is the same as 1 over 10 centimeters, is the same as 1 over 1000 meters. So you can work with that to see what that volume is in cubic meters. Please try it out and let's see what you end up with. Yes? Here is another one. The density of liquid mercury is 13,600 kilograms per meter cubed. So kilograms per meter cubed, that's how we write per meter cubed. Express this value in grams per centimeter cubed. Okay, so this is how we go about this. So 13,600 kilograms per meter cubed. So this means the same thing as this. So it's nicer to write it in the same line that way. Makes life really nice, especially with the typesetting. Now we want to change that to grams. So this is in kilograms. We don't want kilo. We want grams. And we don't want meters cubed. We want centimeters cubed. So the first thing we want to remember is that kilo means 1000. So we can replace the k there with 3 zeros. Okay, or multiply by 10 power 3. And then we need to change the meter cubed into centimeter cubed. 1 meter is 100 centimeters. So 1 kilogram is the same as 1000 gram, because the k there is 1000. So I'm going to remove the kilo there and I'm going to put 1000 grams. Okay, similarly 1 meter is 100 centimeters. So if I want cubed there, then I have to cube both sides. So 1 meter cubed is going to be 100 cubed, which is 1 million centimeter cubed. Okay, so that 1 meter cubed becomes 1,000,000 centimeters cubed, as you can see. And so where there is 1 meter cubed, I'm going to remove and put 1,000,000 centimeter cubed, and that is down there. So I can therefore write this as 13,600 multiplied by, up there I'm going to put 1000 grams, and at the bottom I'm going to put 1,000,000 centimeter cubed, like that. And now the 3 zeros here can disappear with 3 zeros here, like that. And these 3 zeros can move the decimal point back 3 steps. So I'm using dotted line there to imply that I'm moving the 0 backwards 3 decimal places because I've cancelled those 3 zeros. And I will end up with 13.6 grams at the top and centimeter cubed at the bottom, which we write as 13.6 grams per centimeter cubed, like that. And that's how you answer this question. Okay, I believe this brings us to the end of this video. I hope that you are able to understand what's going on. If you liked the video or you found it useful, please consider sharing it with others who might also need some help with this. Also, if you are seeing this video for the first time, please consider subscribing and hit the notification sign so that any video that we post, you will be notified as quickly. Okay? Please share widely, like the videos, put comments in the comment section. If you need additional help or you have a question, please don't hesitate to contact me. Thank you. I'll see you for the next video, when we will pick a selected number of questions from the worksheet and solve them. All right? If you ask your relevant questions before that, I can include them in the next video. All right? Thank you very much. I'll see you in the next video. Bye.